Hey everybody, we are looking at power, one more term that we're going to be using during our unit of energy and its conservation. Luckily, this is pretty quick, no new major idea or concept, just really a simple equation. Okay? To start us off, I want to present to you a certain scenario. And the scenario is this. My first car, a 2002 Saturn sedan, mostly made out of plastic, it could start from rest, and it could reach 0 to 80. Okay, it could go 0 miles an hour, not moving, to 80 miles per hour. Likewise, a 2017 Tesla can also start at rest and reach 80 miles per hour. Well, based on that, both of these cars are equal. That's what you would have to determine, right? I mean, even if we looked at like the work done by the engines, we know that work done is going to equal delta K, at least the net work done on the car. So that's 1/2 mv squared minus 1/2 mv naught squared. Well, both cars are starting at rest, so that goes away. All right, well, they both reach the same velocity, 80 miles per hour, for example. Yeah, they might have a different mass, but they still are going to have almost essentially the same energy. To be honest, my brother's old car, a Lincoln Continental, was much more massive. It could also go 0 to 80. But that's going to be the same or even more work than a Tesla, which can fly off the line? Something doesn't seem to be enough. A lot of people would agree that a Tesla, its engine, is able to do a lot more than an old 2002 Saturn. And not just maybe because one has more mass than the other. But looking at our equation so far, the work done, how much energy these engines can apply, well, it doesn't seem to be based on anything except for the change in velocity and, like I said, the mass. So something else must be at work. Why is a Tesla or a Camaro or a Dodge Viper or a Lamborghini, why do people buy those cars? Because they're so much faster and more interesting, right? If they're able to do the same amount of work. Well, the difference isn't in how much work they're doing. It's all about how quickly they are able to do that work, how quickly. Turns out that's the key, not how much work is done, but how fast that engine is able to make that car speed up. All right? So really, we want a way to compare how fast, how quickly work is done. And that's where this term power comes into play. Power, by definition, is the rate work is done, how quickly work on an object is completed. Okay, the symbol for power, well, that's uppercase P. The equation, power is equal to the work divided by time. It's as simple as that. Or P equals W over T. The units for power? Well, they have to be the units of this equation. So work is measured in joules. Time is measured in seconds. Joules per second. That's the unit. This is also given its own name called a watt, W-A-T-T. Sometimes abbreviated, just uppercase W. W is work, it's weight, and it's watts, to make it nice and confusing. So power, simply, it's how much work is done over time. If we were looking at, say, the net power, or the power done from the net work, well, we would do W net over T. And all of our original things involving work are still true. This could be how quickly an object's kinetic energy changes, because this is the work energy theorem, work net to delta K. Essentially, power is just taking the work being done, dividing it by the time. All right? And a Tesla or a Lamborghini has a much more powerful engine compared to my old Saturn sedan. So that's why you might consider a Lamborghini, why its engine is superior. It has way more power. It's able to go 0 to 60 in a much faster amount of time. That's it. Power. Easy as that. Thanks. Bye.